All right, welcome to the Explainer. Today, we get to play Techno Detective. We're going to dive into a real-world technical mystery using an actual service log to figure out what brought a super high-tech, very expensive machine to a dead stop. And this isn't some textbook example. Nope. This is a step-by-step diagnostic journey, and our goal is to find one tiny little fault buried in a mountain of complexity.
So it all kicks off with this really cryptic message from a $1 million machine. Regulación de velocidad en tope e Ireal igual 0, which basically translates to speed regulation at limit and real current equals 0. That's it. That's the only clue our technician has to go on. You could almost think of it as a digital cry for help, and now we have to figure out what on earth it means.
All right, Section 1, Machine Down, Error 7. Let's set the scene. Imagine this, it's late at night, you're in a high-precision manufacturing facility, and everything has just ground to a halt. Silence.
And believe me, the pressure is on. The log shows the fault hit just after 11 p.m. Now, by the time our technician, a guy named Fabien Acheval, gets on site, it's already after 1 in the morning, and the entire production line is just waiting. You gotta understand, every single minute of downtime here costs a ton of money. So, what does that cryptic message, that error 7, actually mean? Well, if you crack open the service manual, it's telling you something pretty specific. It means the speed controller is pushing as hard as it possibly can. It's at its absolute limit, but it's getting nothing back. Zero electrical current. The command is going out, but there's no response, no feedback at all. Yeah, you can think of it like this. The brain of the machine can't hear its own muscles anymore. It's shouting commands at the motor, telling it to move, but all it gets back is absolute silence. It's like shouting into a void. So, to solve this mystery, our techno detective has to first understand, well, how are these parts supposed to talk to each other in the first place?
And that brings us right to Section 2, the control loop mystery. See, to crack this case, you really have to get your head around a core concept that's behind, well, almost any automated system you can think of. It's called the control loop.
So what is a control loop? Well, think of it like the cruise control in your car, but for something that needs microscopic precision. It's basically a constant self-correcting conversation. You know how your car's cruise control measures your speed, compares it to what you set, and then adjusts the throttle? It's that same idea, a continuous cycle to maintain a perfect state, whether that's speed, or in our case, the exact position of a cutting tool.
Okay, so let's break this down. At its most basic, the control loop is like a 4-step conversation. And this conversation is happening thousands of times every single second. Step 1. The main CNC computer sends a command, something like, hey, move to this exact spot. Step 2. The controller translates that command into an electrical signal. Step 3. The motor actually moves. And finally, Step 4. A little sensor called an encoder reports back saying, okay, I'm here now. The system sees any tiny difference and corrects it instantly.
But here's where it gets really interesting. It's not just one simple loop. It's actually a set of loops nested inside each other. You've got the big one, the position loop. That's like the master plan. Where should I be? But inside that, you have the speed loop, kind of like a manager asking, how fast should I get there? And nested even deeper is the current loop, which is the muscle, constantly figuring out how much power do I need to apply right now.
And that is why our error message is such a huge clue. That Ireal equals 0, or real current equals 0, it's pointing directly to a breakdown in the current loop. The innermost, fastest, most fundamental loop of them all is completely broken. The system has no idea how much electrical power is flowing to the muscle, and without that feedback, the whole thing just shuts down for safety. So now our technician knows exactly where to start looking.
Okay, Section 3, a technician's investigation. So armed with this knowledge, our detective Fabien starts the real hands-on work. He's moving from the system's digital brain to its electrical heart.
So where do you start? Well, with the classics, right? You turn it off and on again. He resets the whole CNC controller, but nope, the fault comes right back. Then he checks the diagnostic screen, and this is interesting. It shows the position error is a flat 0, and that is a massive clue. It means the system isn't even trying to make a correction because it already knows something is fundamentally broken. All right, so software checks are a dead end. It's time to get hands-on. He's got to open up the electrical cabinet. Now this next part is tricky, and you got to know what you're doing.
He carefully bypasses a safety system so he can power up the drive module without actually turning on the motors. This lets him take a direct electrical reading from the heart of the system. It's a delicate and frankly a pretty dangerous step.
And this is it. This is the aha moment. He hooks up his multimeter, and what he's expecting to see is a nice, lively, fluctuating signal, bouncing around 500 millivolts. That would show the controller is working. But what does he actually see? A flat 3 millivolts. Basically, nothing. It's the electrical equivalent of a flat line. The conversation is dead.
And that brings us to section 4, the fix and the finish. Because with that electrical flatline confirmed, all the evidence is suddenly pointing away from some complex fried component and towards something much, much simpler.
See, the problem wasn't a broken part. The electrical conversation had just stopped. So the fix, it was purely physical and very methodical. First, power down the entire system. Then systematically unplug the main control board. Unplug the customization board. Disconnect the motor's main signal cable. And then you firmly reconnect everything. The suspicion is a simple poor contact, maybe from years of vibration or heat cycles. So everything's plugged back in, he powers the drive back on, takes a deep breath, and measures again. And there it is. A beautiful, healthy, oscillating 500 millivolts on the meter. The signal is back, the connection is restored. The brain can finally hear the muscle again.
Now that the control loop is talking again, the technician can remove the safety bypass, enable the servos, and run a full test cycle. And just like that, the machine whirs to life, machining a perfect test part completely flawlessly. And get this, by 1:53 a.m., less than an hour after he even arrived on site, the case is closed.
So it really makes you think, right? When a complex system like this fails, is the solution always going to be complex? This case teaches us a huge lesson. A multi-million-dollar, incredibly precise machine was brought to its knees by, what? A loose plug. A microscopic break in a connection. It's just such a powerful reminder that, in this world of insane complexity, you can never ever forget to check the simple stuff first. Sometimes, the most sophisticated problem has the most fundamental solution.